variations, changes in the nature of the Earth's surface, and this is kind of a plate tectonic explanation, if you like, related to the accumulation of supercontinents and superoceans versus dispersed continents and relatively smaller oceans, although their total surface area doesn't change significantly. In other words, about 70% of the world through the Paleozoic was oceanic and 20-25% continental. But depending on how you clump the continents together or break them apart, you obviously change the nature of the Earth's surface when you do that. And then, perhaps more interestingly from our perspective today, changes in atmospheric composition is a major player in the climate game. So if we look at astronomical variations to explain some aspects of climate variation, I'm not quite sure where they get this information from, but the argument is that there is a change in the frequency and or intensity of the solar radiation source. In other words, the amount of energy coming from the sun. And the argument is that there has been a change over time, and that the change is dominantly in one direction, and that is an increase in the solar radiation reaching the planet on the order of about 1% per 80 million years. And that presumably is tied to the evolution of the sun itself. These things are supposed to burn out over however many billions of years they last. And so whether that is a relatively linear process or whether fluctuations in that, I don't know. But certainly solar radiation would be an important component of any astronomical variation we might see. But more likely and somewhat easier to recognize smaller scale orbital perturbations in the planet with respect to where the planet is with regard to the sun, because the sun being the principal source of energy, at least on the surface of the planet, that's important. So if the Earth was orbiting the sun for example, in a perfectly circular orbit, and the planet itself was orbiting orthogonal to the plane of the orbit around the sun, in other words, if the planet wasn't tilted, then a lot of the kind of variation that we are talking about here related to orbital perturbations wouldn't apply, and you would have a much more constant climatic situation than we observe, and that is the variation that we do see is in fact tied to the fact that the planet does not orbit in a perfect fashion around the sun. So if we look at these different parameters that can influence climate, there are three orbital variation patterns that we see. Eccentricity, and that on the upper diagram there essentially relates to whether or not the planet orbits the sun in a perfectly circular motion, and the fact is it doesn't. The orbit is slightly eccentric. The second characteristic is the obliquity characteristic, and that has to do with the fact that the Earth is orbiting about its axis, its rotational axis, and that rotational axis is tilted with respect to the plane of the rotation around the sun. And that has an influence. And finally, precession, that tilting of the planet about its rotational axis essentially wobbles, and that's what precession is. And that wobbling makes a difference. Now, how does this work? Well, what all of these things mean in reality is because of these little perturbations and these differences at different times under different circumstances, the planet or parts of the planet will be either closer to or further away from the sun. Now the difference in terms of total number of kilometers is probably not that great, but the fact is those differences are sufficiently are of a sufficient magnitude that the amount of solar radiation received by the planet, or the part of the planet that is either closer or further away from the sun, makes a difference in terms of the climate. And you'll notice on here there are cycles labeled under eccentricity, for example, 95,000 years, 123,000, and 413,000 years, because these things, the irregularity of the orbital parameters that we are talking about here are in and of themselves predictable, so that they will occur at a certain cyclic rate, and so obliquity has a 41,000 year cycle, precession has a 19,000 and a 23,000 year cycle associated with it. And on the left there you have the three, the electricity, the obliquity, and the precession, showing you how these things vary. And let me get the pen activated here. The upper part of the diagram up here is a measure of the ellipticity, the obliquity, and the precession, and you see that these occur in a cyclic fashion, and they measure the insulation effect of those cycles measured in watts per square meter. That's the energy level that you measure. And so each of these parameters has its own cyclicity, obviously, and obviously they interact with each other, either reinforcing or cancelling each other out. And the end product, which is B, okay, is the combined effects of those three orbital parameters expressed in terms of temperature, watts per square meter, either higher or lower wattage per square meter, depending on whether the combined effects are moving part of the planet away from the sun or closer to the sun. So, if you're familiar at all with astronomical texts on climate, you will see them in terms of Milankovitch cycles. People talk about Milankovitch cycles. Those are related to these kind of orbital parameters. The second factor that can influence the climate is the change in the nature of the Earth's surface. And I don't know that that bullet there is correct in the sense of changes in the total area of land. The total area of land will vary, of course, because if you flood the land, you cover it with parts with water. But the overall continental versus oceanic relationship on the surface of the planet, certainly through the Paleozoic, probably has not changed much. In other words, the 70, 75%, 25, 30% continent, 70, 75% water hasn't changed. But clearly, during times of high stands of sea level, mostly related to the change in volume of the mid-ocean ridges that we talked about in class on Monday, will affect the total area of land that's exposed. And that's the reason why exposure of the Earth's crust is important. Will be made clear a little bit later. So it's probably more important to think of this in terms of the geometry and distribution of ocean basins and continents, and how that affects ocean circulation patterns. The ocean, the world's oceans are extremely important, obviously, in affecting the climate, because the circulation of water through the world's